Hello everyone, Mr. Fawcett here, and we're back with another AP Calculus lesson. Today begins our discussion of differential equations, which brings the topics of derivatives and integration together to help us solve equations that we really haven't been exposed to yet. So first thing I'm going to do is just kind of give you an example of what a differential equation is, and then we'll talk about what the solutions to those look like, and then we'll finally talk about how to tell if something is a solution or if it's not a solution. So let's get a clean page actually. There we go. So maybe you can tell from the name, but a differential equation is going to be an equation that has a derivative in it, at least one. So I'm just going to throw some examples here. I could have a differential equation that looks like this: f prime of x plus x squared is equal to f of x. I could have something like y prime minus y double prime is equal to 6y minus 3. I could have dy dx minus x is equal to 4y. Or I could have something like this, 3 d2y over dx squared is equal to 4 dy 4 dy dx minus x. So as you can kind of tell, these equations have both original functions in them as well as derivatives, and some of them even have second derivatives in them. So all a differential equation is, it's an equation that relates an original function to one or more of its derivatives. When you solve these equations, right? When I solve an equation with, just x's in it, like x minus 3 equals 10, right? That's going to give us a number. X is equal to 13. Sometimes you can even get, multiple solutions, right? If I have x squared is equal to 4, well, then I can get x is equal to plus or minus 4. Sometimes you can have infinite solutions, right? Sometimes you can have no solutions. But the equations that we've solved up to this point, we've gotten numbers as solutions. For differential equations, the solutions to a differential equation are functions. So when I solve a differential equation, and you really don't know how to do that yet, which is okay, we're just kind of breaking into this. But when I solve one of these differential equations, I am going to be finding the original function. So up here for the red, I would be finding out what the function f of x looks like. For the pink, I'd be finding what the function y looks like. So y equals something. Same thing for the blue. I'd be finding out what the function y looks like. And same thing for the orange, actually. I'd be finding out what the function y looks like. Again, it just depends on how it's written, right? If it's written as f of x, then you would just call your solution a function f of x. If it's in terms of y, you would just call it, your function of y. But the point being, solutions to differential equations are just the initial function. And you'll see that you could have an infinite number of solutions, right? And this kind of gets into when you take an antiderivative, right? If I take an antiderivative of, let's just go with 4x, right? My solution there is 2x squared plus c, where that c could be any constant. And you'll see that to solve a differential equation, we will have to use integration at some point, which means we could have an infinite number of solutions depending on what that constant is. But again, two key parts from this little introduction. One, a differential equation is an equation that relates an original function to one or more of its derivatives. and that the solutions to differential equations are functions, not just numbers. Okay. Well, let's go back up to the top. That kind of answers the first question. It says when we solve a differential equation, what does our solution look like? What is its relation to the differential equation other than that it's a solution? Solutions are functions specifically the original function. So all we're going to do today is verify whether a function is a solution. You're not going to be finding the solution on your own, but you're going to be given a possible solution and deciding whether it's an actual solution or not. Later down the road, in later lessons, we will go through the actual process of coming up with those solutions on our own. But today, all we're focused on is verifying whether a function is a solution or not. So let's start off with this first one. Is y equals 4x a solution to the differential equation below? Show your work to explain why or why not. Okay, so you can pause the video if you want and see if you can verify this. I don't know if it's very clear what direction to take because these equations are new for you. But let's take a look at the given information. So I know that the possible solution is y equals 4x, and I have my differential equation right here. Well, it would probably help if I rewrote everything in terms of x's or y's. And because this first equation or function up here is already solved for y, I'm going to replace the y in my differential equation with 4x. So dy dx is equal to 4 times 4x over x. You could simplify. So dy dx is equal to 16, right? These x's are going to simplify. So what about this dy dx? Is there any way I could figure out what that's supposed to be, right? Because the differential equation says it's supposed to be 16. But is there anything I could do with that possible solution up here? This y equals 4x. Well, what if I took the derivative with respect to x, right? Y is equal to 4x. If I apply the derivative operator, so d dx to both sides, well, on the left-hand side, I'm going to get dy dx. On the right-hand side, I'm just going to get 4. So our possible solution says that dy dx is supposed to be equal to 4. So I can replace dy dx with 4, and I get 4 is equal to 16. This is obviously not true, false. So y equals 4x is not a solution. Let's try another one. Let's try another possible solution. And this time I think you could probably pause and attempt this one on your own, see what you get, and see if it makes sense for whether it should be a solution or not. Okay, so same thing. I'm going to rewrite my differential equation in terms of x's. So instead of 4 times y, I'm going to get 4 times x to the 4th all over x. And you could simplify now, or you could replace the dy dx now. I'm just going to replace the dy dx now, and then we'll simplify afterwards. So y is equal to x to the 4th. If I apply that derivative operator to both sides, that is going to get me dy dx is equal to 4x cubed. So I can replace dy dx with 4x cubed. And then I can simplify and see if I get the same thing on both sides. So 4x cubed. On the right-hand side, when I simplify the denominator with the numerator, I do indeed get 4x cubed. This is true, which means our possible solution is an actual solution. Because whatever number I substituted in for x in this function or equation right here, it's going to work in my differential equation. Again, we're just practicing today, so we're going to take a look at the one below. It is written a bit differently, so instead of dy dx, we have f of x and f prime of x. So is f of x equals 2x a solution? Think about why or why not. Go ahead, pause the video, see if it works. Okay, so f of x is equal to 2x, so I can replace that in my differential equation. And you could simplify now or later, it doesn't matter. So that gives me f prime of x is equal to just x. Well, if f of x is equal to 2x, that means f prime of x should be 2x should be equal to 2. So from my possible solution, I get f prime of x is equal to 2. So if I substitute that in, I get 2 is equal to x. Now, here's the thing. You may think, well, I got an answer, right? I got x is equal to 2. That's not something that's doesn't look like it's false, right? It's not like 2 is equal to 4 false, but it's also not an identity. So take a look at what these two things are saying. So we have the given possible solution. When I take the derivative of that, that says that f prime of x is equal to 2. As I'm breaking down my differential equation, though, I get an equation that says f prime of x is equal to x. Well, those are not the same, right? One of those is saying the derivative is always equal to 2. One of those is saying, excuse me, the derivative can change based on what x is. So essentially, this function right here, this is a solution when x is equal to 2, but otherwise it's not a solution. So is it a solution to the differential equation? No, because the solution to the differential equation has to work for every possible x value of the original function. And here, again, the only x value that this function works for is x is equal to 2. So you need to get an identity when you're verifying solutions for it to be a solution to the equation. It can't just be like x is equal to 4, x is equal to -3, because that means that that particular solution only works in one instance. But we need it to work for any value of x in the domain of the original function. So let's fill in these blanks below to kind of sum that up. Remember, the solution to a differential equation is a function, not a single point. Thus, the function needs to work for all possible values of x. And it's all possible values of x in the domain of the original function. So if that domain is constricted at all, then it wouldn't have to work for any value of x, but it would still be more than 1, unless the domain of that function was just a single x value. Okay, I think we may stop the video here. Basically, we're just going to be doing the same thing with the rest of these problems. Can we, get an identity when we make our substitutions in the differential equation? If we can, then we know that that given solution is an actual solution. If we get anything other than an identity, then we know that it's not going to be a solution. So as always, enjoy the rest of your day, and we will look forward to seeing you next time.